Before tonight's journey begins, take a moment to imagine the vast distance between Earth and the icy world of Pluto. It appears as a tiny point of light at the edge of our solar system, yet reaching it is far more difficult than most people realize. How long would it really take humans to travel to Pluto? A few years, a few decades, or much longer than anyone expects? The answer reveals surprising truths about distance-speed technology and the enormous scale of space itself. In this video, we will follow the path from Earth to Pluto, compare past spacecraft missions, explore the challenges of deep space travel, and discover what a future human journey might actually look like. If fascinating space documentaries help with relaxation, learning, and sleep, please take a moment to like this video, subscribe to Cosmic Bedtime Stories, and join us for many more peaceful journeys through the universe. Now, as the stars slowly drift across the darkness, the long voyage to Pluto begins. Pluto occupies one of the most distant known regions of the solar system. Far beyond the bright worlds that can easily be seen from Earth, beyond the familiar paths of the major planets, it travels through a cold and dim realm where sunlight is greatly reduced and distances become difficult to imagine in ordinary human experience. The question of how long it would take humans to reach Pluto begins with an understanding of where Pluto actually is. Before any spacecraft can be imagined, before any engines can be considered, the vast scale of the destination itself becomes the first reality that shapes every part of the journey. Pluto moves around the Sun in an elongated path that carries it through the outer solar system. For much of its orbit, it remains more than 5 billion kilometers from the Sun. At some points it comes somewhat closer, at others it moves even farther away. The exact distance between Earth and Pluto changes constantly because both worlds travel around the Sun at different speeds and along different paths. Sometimes they are positioned on roughly the same side of the solar system. At other times they are separated by the Sun itself, placing even greater distances between them. From Earth, Pluto appears as an extremely faint point of light. It cannot be seen with the unaided eye. Even large telescopes reveal only a tiny object. For many decades after its discovery in the year 1930, Pluto remained little more than a distant speck. Astronomers could calculate its orbit and estimate some of its characteristics, but the world itself remained largely mysterious because of the enormous distance involved. Distance in the outer solar system often exceeds ordinary intuition. Human beings spend their lives moving across landscapes measured in meters, kilometers, and occasionally thousands of kilometers. Aircraft cross continents in hours, ships cross oceans in days or weeks. Even journeys around Earth remain small when compared with the distances separating planets. Pluto exists on a scale where familiar comparisons begin to lose their usefulness. Light itself requires time to travel. Light moves faster than anything known in nature, crossing nearly 300,000 kilometers every second. Yet even light cannot reach Pluto instantly. Depending on the positions of Earth and Pluto in their orbits, sunlight reflected from Pluto may require several hours before it arrives at Earth. When astronomers observe Pluto through telescopes, they are not seeing the dwarf planet as it exists in that exact moment. They are seeing it as it appeared several hours earlier. This delay offers a gentle introduction to the immense scale involved. If light moving at the fastest known speed in the universe requires hours to bridge the gap, then physical travel becomes a far greater challenge. Any spacecraft must contend with distances that make even the largest regions of Earth appear tiny by comparison. Pluto belongs to a region known as the Kuiper Belt. This broad zone contains countless icy bodies that orbit beyond Neptune. The Kuiper Belt represents a vast reservoir of frozen material left over from the formation of the solar system. Pluto is one of its largest known members. It shares this distant environment with many other worlds, some smaller and some approaching similar sizes. The Sun dominates the solar system through gravity, but its visible influence changes with distance. Near Earth, sunlight is bright enough to illuminate landscapes, warm oceans, and support life. At Pluto, sunlight becomes far weaker. The Sun still shines, but it appears much smaller in the sky. Daylight on Pluto resembles a bright twilight compared with the sunlight experienced on Earth. This gradual fading of sunlight illustrates how far Pluto lies from the center of the solar system. Every increase in distance spreads the Sun's energy across a larger area. As Pluto travels through its orbit, it receives only a small fraction of the sunlight reaching Earth. Temperatures remain extremely low. Ice behaves differently in such conditions. Materials that appear as gases near Earth may freeze solid in Pluto's environment. The dwarf planet itself measures roughly 2,300 kilometers across. Compared with Earth, it is small. Its diameter is less than 1/5 that of Earth. Yet despite its modest size, Pluto commands attention because of its location. Its remoteness transforms it into one of the most challenging destinations ever explored by spacecraft. Pluto also possesses a remarkable system of moons. The largest, Charon, is unusually large relative to Pluto itself. The two bodies orbit a shared center of motion located between them. This creates a relationship unlike that seen between most planets and moons in the solar system. Smaller moons accompany them, moving together through the darkness of the outer solar system. From the perspective of Earth, Pluto spends nearly 250 years completing one orbit around the Sun. Since its discovery, it has not yet completed a full orbit. Human civilizations experience generations within the time required for Pluto to circle the solar system once. This slow movement reflects the immense size of its path. Astronomers often describe the solar system as mostly empty space. The statement becomes especially true in Pluto's region. The distances separating objects grow enormous. A spacecraft traveling outward encounters long stretches where little changes from day to day. The Sun gradually shrinks. Planetary encounters become increasingly rare. Vast expanses of space dominate the voyage. Understanding Pluto, therefore, begins with understanding separation. The dwarf planet is not merely another world waiting at the edge of a map. It occupies a distant frontier where the scale of the solar system becomes fully apparent. Every estimate of travel time, every engineering decision, and every future dream of human exploration must first confront the simple fact that Pluto is extraordinarily far away. Its distance is not an obstacle that appears later in the story of exploration. It is the defining condition from the beginning. The outer solar system establishes the challenge before a spacecraft ever leaves Earth. The destination itself shapes every possibility. Pluto remains a small, icy world moving through darkness and faint sunlight, separated from Earth by billions of kilometers and by a scale of distance unlike anything encountered in ordinary life. The distance to Pluto becomes easier to understand when it is measured carefully rather than imagined. Human experience offers few useful comparisons for billions of kilometers. Roads, oceans, and continents provide scales that feel familiar, but the solar system operates on dimensions so large that ordinary measurements quickly become cumbersome. Astronomers therefore rely on methods that transform these immense separations into forms that can be compared and studied. One of the most useful measurements in planetary astronomy is the astronomical unit. This unit represents the average distance between Earth and the Sun. It serves as a convenient ruler for describing locations throughout the solar system. Instead of constantly speaking of hundreds of millions or billions of kilometers, astronomers can describe planetary distances as multiples of Earth's average distance from the Sun. Earth occupies a position of approximately 1 astronomical unit from the Sun. Jupiter lies about 5 astronomical units away. Neptune travels at roughly 30 astronomical units. Pluto moves through a region that generally places it around 40 astronomical units from the Sun, though its elongated orbit causes this distance to vary. By using the astronomical unit, the structure of the solar system becomes easier to visualize. The inner planets occupy a relatively compact region. The outer planets spread across far greater distances. Pluto resides in a realm that stretches much farther still. Even with this simplified ruler, the true scale remains difficult to grasp. If Earth and the Sun were separated by only 1 meter, Pluto would still be dozens of meters away. The space between them would contain vast empty regions. The planets themselves would become tiny points scattered through an enormous volume. Most of the solar system consists not of worlds, but of separation. Travel time depends directly upon distance and speed. On Earth, people often think of travel in terms of hours or days. A vehicle moves at a certain speed and covers a known distance. The same principle applies in space, but the distances become so large that the results are measured in years. A spacecraft traveling outward must continue moving for extraordinary periods before reaching the outer solar system. The challenge becomes clearer when familiar speeds are compared with planetary distances. A commercial aircraft can travel several hundred kilometers in an hour. At such a speed, reaching Pluto would require many centuries. Even the fastest aircraft ever built would require an impractical span of time. The atmosphere of Earth limits aircraft design, and such vehicles are not intended for interplanetary travel. Nevertheless, these comparisons reveal the enormous difference between human transportation on Earth and travel through space. Spacecraft operate at much higher speeds than ordinary vehicles. Modern planetary probes can travel tens of thousands of kilometers per hour. Even so, the journey remains long. Distances measured in billions of kilometers continue to dominate the calculation. A spacecraft may travel faster than any machine moving across Earth's surface, yet Pluto remains years away. Astronomers also use the travel time of a light as a measurement. Because light moves at a known speed, its travel time immediately reveals distance. When sunlight reaches Earth, it has already spent about 8 minutes crossing space from the Sun. Pluto lies much farther away. Signals travelling between Earth and Pluto require several hours. This means that communication itself becomes part of the challenge of deep space exploration. If a command is transmitted from Earth toward a spacecraft near Pluto, the signal does not arrive immediately. It travels through space at the speed of light and still requires hours to complete the journey. A response requires additional hours. Conversations that feel instantaneous on Earth become impossible across such distances. Every exchange becomes a patient process governed by the finite speed of light. Measurements of distance also reveal why planetary alignment matters. Earth and Pluto do not remain fixed. Both travel continuously around the Sun. As they move, the distance between them changes. A mission launched during one period may encounter a shorter route than a mission launched during another. Engineers therefore calculate trajectories with great care, seeking opportunities that reduce travel time and energy requirements. The shape of Pluto's orbit introduces another layer of complexity. Unlike the nearly circular paths followed by some planets, Pluto's orbit is noticeably elongated. During part of its journey, it moves somewhat closer to the Sun. During another part, it retreats farther into the outer darkness. The position of Pluto along this orbit affects the total distance a spacecraft must travel. Distance alone, however, does not determine travel time. The path taken matters as much as the destination. A straight line drawn between Earth and Pluto may appear simple on paper, but real. Spacecraft do not travel through a static solar system. Every world moves continuously. Earth changes position during the voyage. Pluto changes position as well. Engineers must calculate where Pluto will be years into the future. rather than where it appears at the moment of launch. This process resembles aiming not at a stationary target but at a moving one. A spacecraft leaves Earth and follows a carefully planned trajectory designed to intersect Pluto's future location. The journey therefore becomes a problem of motion timing and celestial mechanics. Celestial mechanics is the study of how gravity governs the movement of objects through space. It provides the mathematical framework that allows missions to reach distant destinations with remarkable precision. Measurements also reveal an important truth about exploration. The solar system is not simply large, it grows dramatically larger toward its outer regions. The distance from Earth to Mars may seem immense, yet Pluto lies many times farther away. Each outward step increases the scale significantly. Travel that appears manageable within the inner solar system becomes far more demanding when extended toward the Kuiper belt. The numbers themselves tell a quiet story. They show that Pluto is not unreachable. Modern spacecraft have already travelled there, yet they also demonstrate that distance remains the central fact governing every mission. The outer solar system imposes patience. Even with powerful technology, travel unfolds across years rather than days or months. Measuring the journey reveals that the challenge is not merely technological, it is geometric. Pluto occupies a distant place within a vast gravitational system, and every kilometre between Earth and that distant world must ultimately be crossed. Earth serves as the starting point for every journey toward Pluto. Although attention often focuses on the destination, the nature of the departure point plays an equally important role in determining travel time. Earth is not a stationary platform resting quietly in space. It is a moving world travelling around the Sun while rotating on its axis, carrying oceans, continents, atmosphere, and every spacecraft ever launched by humanity. From the surface, Earth appears stable. Mountains remain in place, seas occupy familiar basins, the horizon rises and falls with the landscape. Yet beneath this calm appearance, Earth participates in several forms of motion simultaneously. It rotates once every day, creating the cycle of daylight and darkness. At the same time, it moves around the Sun at tremendous speed, completing one orbit each year. The solar system itself moves through the Milky Way galaxy, adding another layer of motion. For missions to Pluto, the most important of these movements is Earth's orbit around the Sun. This orbital motion provides an advantage. A spacecraft launched from Earth already possesses the speed that Earth carries around the Sun. The vehicle does not begin from rest. It starts the journey while sharing the planet's existing motion. Engineers take careful account of this fact when designing missions. The direction of launch and the timing of departure influence how effectively Earth's motion can contribute to the spacecraft's trajectory. Earth occupies a region relatively close to the Sun. At an average distance of 1 astronomical unit, it receives abundant sunlight and warmth. The environment that supports life also shapes the conditions under which spacecraft are built and launched. Rockets rise through a thick atmosphere carrying instruments and fuel away from a world dominated by gravity and air resistance. Every journey toward Pluto begins within this environment. Gravity defines the first challenge. Earth contains enough mass to hold ocean's atmosphere and living organisms securely to its surface. The same gravitational pull resists the departure of spacecraft. Reaching orbit alone requires significant energy. Before a mission can travel toward the outer solar system, it must first overcome Earth's gravitational influence sufficiently to operate in space. The planet's atmosphere adds another layer of complexity. Air creates drag, a force that opposes motion. Rockets consume large amounts of fuel during the first minutes of flight because they must climb through this atmosphere while also accelerating. Once they reach space, conditions change dramatically. The atmosphere fades away and movement becomes governed almost entirely by gravity and momentum. Momentum refers to the tendency of a moving object to continue moving. In space where resistance is extremely low, momentum becomes especially important. A spacecraft that reaches the proper speed can continue traveling for years without requiring constant propulsion. Small adjustments may be necessary, but much of the journey relies on motion, acquired during launch and later gravitational interactions. Earth's orbit introduces an important consideration for interplanetary travel. Since Earth moves continuously around the Sun launch, opportunities are not identical every day. The geometry of the solar system changes from month to month and year to year. Engineers calculate specific windows during which a spacecraft can depart efficiently toward a chosen destination. Missing such a window may require waiting for another favorable alignment. This reality reflects the dynamic nature of the solar system. Planets do not sit on fixed tracks like markers on a map. They move constantly through space. Earth occupies a different position every day. A mission to Pluto therefore begins not only from a particular location, but also from a particular moment. Time and position become inseparable. Viewed from afar, Earth appears as a small blue sphere illuminated by sunlight. Clouds swirl above oceans. Ice covers polar regions. Continents drift slowly over geological timescales. Yet despite its modest appearance against the vastness of space, Earth remains one of the most favorable launch sites imaginable. It possesses abundant materials, energy resources, and a stable environment in which complex technology can be developed. The Moon also plays a subtle role in Earth's space environment. Orbiting at an average distance of several 100,000 kilometers, it influences tides and contributes slightly to the gravitational conditions experienced by spacecraft departing Earth. While missions to Pluto do not rely directly on the Moon, its presence forms part of the broader system surrounding the planet. Earth's magnetic field extends outward into space, creating a protective region that shields the surface from many charged particles arriving from the Sun. Spacecraft leaving Earth eventually pass beyond much of this protection. The transition marks a movement from the familiar environment of near-Earth space toward the wider conditions of interplanetary travel. Humanity's experience with space exploration begins here. Every robotic probe sent to the outer planets, every telescope placed beyond the atmosphere, and every mission that ventures into deep space originates from Earth. The planet functions as both home and launching ground. Its gravity provides the challenge. Its orbital motion provides an advantage. Its position within the solar system determines the geometry of every departure. Understanding Earth as a departure point reveals that a journey to Pluto does not begin in empty space. It begins on a moving world already participating in the larger motions of the solar system. The spacecraft inherits Earth's velocity around the Sun, launches through its atmosphere, escapes its gravity, and carries the influence of its starting conditions far into deep space. Travel time to Pluto therefore depends partly on characteristics established before the spacecraft even leaves the vicinity of Earth. The planet's motion, gravity, and location shape the opening stages of the voyage. Every future human expedition toward Pluto would begin in exactly the same way, departing from a world that circles the Sun, while carrying its travelers outward from a familiar environment into the vast distances beyond. Leaving Earth behind is a process defined by energy. The vast distance to Pluto often attracts the most attention, yet the journey cannot begin until a spacecraft first escapes the strong gravitational influence of its home world. Every kilogram of material that rises from Earth must overcome a force that has shaped the planet for billions of years. Oceans remain in place because of gravity. The atmosphere stays attached to the planet because of gravity. Mountains, rivers, forests, and cities all exist within the grip of gravity. A spacecraft heading toward Pluto must climb out of that grip before it can begin crossing the solar system. The challenge begins on the launch pad. A rocket stands filled with fuel that contains stored chemical energy. During launch, engines convert this energy into motion by expelling exhaust at high speed. The rocket moves upward because the exhaust moves downward. This principle remains the foundation of nearly all spaceflight conducted by humanity. The first moments of flight demand tremendous power. Gravity pulls continuously toward Earth, while the atmosphere resists motion through drag. The rocket must accelerate rapidly enough to counter both effects. Large amounts of fuel are consumed during these early stages because lifting mass away from Earth requires substantial energy. As altitude increases, the atmosphere becomes thinner, air pressure decreases, drag gradually weakens. The rocket continues accelerating, shedding empty fuel tanks and other components that are no longer needed. This process improves efficiency by reducing the amount of mass that must be carried farther into the journey. Eventually, the spacecraft reaches orbit around Earth. Orbit is often described as a state of continuous falling. A spacecraft moves forward so rapidly that as it falls toward Earth, the surface curves away beneath it. The result is a stable path around the planet. Reaching orbit is a major achievement, but it represents only the first stage of a mission to Pluto. Low Earth's orbit remains firmly within Earth's gravitational influence. Gravity there is only slightly weaker than at the surface. Astronauts appear weightless, not because gravity has vanished, but because they are falling continuously around the planet. A spacecraft destined for Pluto cannot remain in orbit. It must acquire additional speed. This additional speed allows the spacecraft to reach what engineers call escape velocity. Escape velocity is the speed required for an object to move beyond the point where Earth's gravity can pull it back into a closed orbit. It does not mean gravity disappears. Earth's influence extends indefinitely across space. Instead, escape velocity provides enough energy for a spacecraft to continue moving away without returning. Achieving escape velocity requires careful planning. Every kilogram of fuel carried into orbit must first be lifted from Earth, yet fuel itself has mass. More fuel requires more lifting capacity, which often requires even more fuel. This creates one of the central difficulties of rocket design. Engineers seek efficient ways to maximize performance while minimizing unnecessary mass. Once escape velocity is reached, the spacecraft begins transitioning from an Earth-centered path to a Sun-centered path. It no longer behaves primarily as a satellite of Earth. Instead, it becomes a traveler moving through the solar system alongside the planets. This transition reveals an important reality about interplanetary travel. A spacecraft does not simply point toward Pluto and fly directly away from Earth. Earth itself moves around the Sun. The spacecraft already possesses Earth's orbital motion at the moment of departure. The goal becomes modifying this motion rather than replacing it. Imagine a runner standing on a moving walkway. The runner already possesses the speed of the walkway before taking a single step. Similarly, a spacecraft inherits Earth's motion around the Sun. Engineers use this existing velocity to help shape the journey outward. The Sun soon becomes the dominant gravitational influence. Although Earth remains important, the spacecraft increasingly behaves as an object orbiting the Sun. Its trajectory is determined by the combined effects of velocity and solar gravity. The path often resembles a long curved arc rather than a straight line. Deep space missions commonly perform additional engine burns after leaving Earth. These controlled firings refine the trajectory and ensure the spacecraft remains on the desired course. Precision is essential because even a small deviation near Earth can grow into a large error after years of travel. The history of space exploration demonstrates how challenging escape can be. Early rockets struggled merely to reach orbit. Decades of technological development gradually enabled missions to the Moon, the planets, and eventually the outer solar system. Each advancement reflected improvements in propulsion guidance systems, materials, and engineering methods. For a human mission to Pluto, the challenge would be even greater. Human travelers require life support systems, living space, food, water, radiation protection, and other necessities. These requirements increase the spacecraft's mass. More mass generally demands more energy. The relationship between payload and propulsion remains one of the most important considerations in mission planning. Leaving Earth also involves psychological distance. From orbit, the planet still fills much of the sky. Continents and oceans remain visible. As the spacecraft moves farther away, Earth gradually shrinks. The familiar world becomes a bright object among countless others. The visual change reflects the physical reality of departure, yet even at great distances, Earth's influence persists. Every spacecraft carries decisions made on Earth. Every trajectory originates there. Every mission toward Pluto begins with the same fundamental challenge of overcoming gravity and entering the broader solar system. The process is neither instantaneous nor simple. It requires enormous energy concentrated into a relatively short period of time. The rocket must accelerate through atmosphere, achieve orbit gain, additional velocity and transition into a solar orbit capable of reaching the outer regions of the solar system. Only after these steps are completed can the longer journey truly begin. By the time Earth fades into a distant point of light, the spacecraft has already accomplished one of the most difficult parts of the mission. It has escaped the gravitational well of its home planet and entered the vast environment between worlds. The road to Pluto remains extraordinarily long, but the first great barrier has been crossed. After escaping Earth's immediate gravitational influence, a spacecraft enters the inner solar system. This region extends outward from the Sun through the orbits of the rocky planets. Although Pluto lies far beyond these worlds, every journey toward the outer solar system must first pass through this comparatively crowded neighborhood. The distances involved remain immense by human standards, yet they are modest compared with what awaits farther from the Sun. The inner solar system is dominated by sunlight. Near Earth, the Sun appears large and bright, providing the energy that supports weather, oceans, and life. Spacecraft traveling outward continue to receive abundant sunlight during the early stages of their voyage. Solar panels operate efficiently. Instruments remain relatively warm compared with conditions in the distant reaches of the solar system. Mercury occupies the innermost planetary orbit. Closest to the Sun, it experiences intense heating during its long days and extreme cooling during its nights. A mission to Pluto does not travel near Mercury, yet Mercury helps define the structure of the inner solar system. It marks the beginning of the planetary region surrounding the Sun. Farther outward lies Venus, a world hidden beneath thick clouds. Its atmosphere traps heat so effectively that surface temperatures become hotter than those found on Mercury, despite being farther from the Sun. Venus demonstrates how planetary environments can differ dramatically even within the same solar system. A spacecraft heading toward Pluto generally remains far from Venus, but its orbit contributes to the constantly changing geometry that engineers consider when planning interplanetary trajectories. Earth follows farther outward, carrying the spacecraft's point of origin behind it. As the vehicle continues its journey, Earth gradually recedes into the distance. At first, radio communication remains relatively quick. Signals travel back and forth in minutes rather than hours. Mission controllers can still monitor the spacecraft with comparatively little delay. Beyond Earth's orbit lies Mars. Known for its reddish appearance, Mars occupies a transitional position between the inner and outer parts of the planetary system. It possesses mountains, valleys, polar ice, and evidence that liquid water once flowed across portions of its surface. For many future exploration plans, Mars represents a major destination. Yet for a mission to Pluto, Mars becomes another marker along the route outward. The space between planets is often imagined as crowded with debris, but most of it is remarkably empty. Tiny particles of dust drift through the solar system. Occasional fragments of rock and ice travel along independent paths. However, the vast majority of interplanetary space contains little matter. A spacecraft spends most of its time crossing enormous regions where almost nothing lies nearby. This emptiness has important consequences. With very little resistance, a spacecraft can maintain its motion for long periods. On Earth, moving vehicles constantly lose energy through friction, with air roads or water. In space, such losses are minimal. Once a spacecraft acquires velocity, it can continue moving for years without continuous engine operation. The Sun's gravity remains the dominant force governing motion throughout the inner solar system. Every planet, asteroid, and spacecraft follows a path shaped primarily by this gravitational influence. Even when a spacecraft is traveling outward, it is still orbiting the Sun. The journey toward Pluto therefore consists of moving from one solar orbit to another, rather than simply flying away in a straight line. Asteroids occupy another important feature of this region. Between the orbits of Mars and Jupiter lies the main asteroid belt, a broad collection of rocky bodies. Popular illustrations sometimes depict this area as densely packed, but the reality is quite different. The asteroids are separated by vast distances. A spacecraft crossing the belt is unlikely to pass near any individual object, unless specifically directed to do so. The asteroid belt offers a useful reminder of the solar system's scale. Even in regions containing large numbers of objects, empty space dominates. Distances between neighboring bodies often remain enormous. The image of planets packed closely together does not reflect reality. Instead, the solar system resembles a collection of isolated islands scattered across an immense ocean of space. As the spacecraft travels farther from the Sun, subtle changes begin to appear. Sunlight remains bright but gradually weakens. Solar radiation decreases with distance. Temperatures experienced by spacecraft components may begin to decline. Engineers design missions carefully to account for these changes, ensuring instruments continue functioning as environmental conditions evolve. Communication distances also increase steadily. Radio signals require more time to travel between Earth and the spacecraft. What begins as a relatively short delay slowly grows longer. Mission operations adapt to this reality by relying increasingly on automated systems capable of performing tasks without immediate human intervention. The inner solar system is also a region where many spacecraft have traveled before. Decades of exploration have produced extensive knowledge about planetary motion, solar activity, and navigation techniques. Missions benefit from this accumulated experience. Engineers can predict trajectories with remarkable precision, allowing spacecraft to cross millions of kilometers while remaining on carefully calculated paths. Despite this familiarity, the distances already covered remain extraordinary. A spacecraft heading toward Pluto may travel farther in a few months than any human traveler has ever experienced directly. Yet in terms of the overall mission, these early stages represent only a fraction of the total journey. The inner solar system occupies the region nearest the Sun, where planets are relatively close together and sunlight remains abundant. Viewed from a broader perspective, the spacecraft is gradually moving away from the conditions that define Earth's environment. The Sun slowly appears smaller. Planetary encounters become less frequent. The surrounding space grows more expansive. The voyage continues through a region that still belongs to the Sun's bright inner domain, but signs of increasing remoteness begin to emerge. The inner solar system therefore serves as a transitional landscape between Earth and the far greater distances beyond. It contains the rocky planets, the asteroid belt, and the familiar environment where most human space exploration has occurred. Crossing this region requires patience and precision. Yet it remains only the beginning of the longer passage toward Pluto. The spacecraft continues outward through sunlight and empty space, steadily increasing its separation from the world where the journey began. Beyond the asteroid belt, the character of the solar system begins to change. The rocky worlds of the inner region give way to a domain dominated by giant planets. Distances become much larger. Planetary systems become more complex, and the scale of the solar system reveals itself more clearly. A spacecraft traveling toward Pluto enters a region where the worlds themselves are enormous, yet the empty spaces between them are larger still. The first giant planet encountered is Jupiter. It is the largest world orbiting the Sun, containing more mass than all the other planets combined. Jupiter is not a rocky planet with a solid surface like Earth. Instead, it consists primarily of hydrogen and helium, the same elements that dominate the Sun. Beneath its cloud tops, pressure increases steadily through layers of gas and fluid-like material. From a distance, Jupiter appears as a banded sphere marked by swirling storms. The most famous of these storms is the Great Red Spot, a vast atmospheric system that has persisted for centuries. Yet for a spacecraft passing through the outer solar system, the most important aspect of Jupiter is not its appearance. It is gravity. Jupiter possesses an immense gravitational field. Its influence extends across a large portion of the solar system. Many spacecraft traveling toward distant destinations use this gravitational power to modify their trajectories. The giant planet acts as a moving source of momentum that can alter a spacecraft's speed and direction without requiring additional fuel. This process becomes one of the most valuable tools in deep space exploration. The environment around Jupiter also demonstrates how dramatically conditions can differ from those near Earth. Powerful radiation belts surround the planet. Dozens of moons orbit within its gravitational domain. Some of these moons possess oceans beneath icy surfaces. Others are marked by volcanic activity or ancient impact scars. Together they form a miniature planetary system within the larger solar system. A journey toward Pluto does not necessarily require a close encounter with Jupiter, but the planet occupies a central position in discussions of long-distance travel because its gravity can significantly reduce travel times. The possibility of using planetary motion to gain speed becomes increasingly important as destinations grow more distant. Farther outward lies Saturn, slightly smaller than Jupiter but still enormous. Saturn is known for its spectacular ring system. These rings consist of countless particles of ice and rock orbiting the planet in a remarkably thin structure. Seen from afar, they create one of the most recognizable sights in the solar system. Like Jupiter, Saturn is primarily composed of hydrogen and helium. Its atmosphere contains powerful winds and complex cloud structures. The planet hosts a large family of moons, including worlds with thick atmospheres and others with frozen surfaces. Saturn's gravitational influence is substantial, though not as powerful as Jupiter's. The distance between Jupiter and Saturn illustrates a key reality of the outer solar system. Even neighboring giant planets are separated by vast expanses of space. A spacecraft may require years to travel from one region to the next. The apparent closeness seen in diagrams often conceals the enormous scale involved. Beyond Saturn lies Uranus. This distant giant differs from Jupiter and Saturn in important ways. It contains larger proportions of substances such as water, ammonia, and methane mixed with hydrogen and helium. Uranus appears pale blue because methane in its atmosphere absorbs portions of sunlight and reflects others. One of the most unusual features of Uranus is its orientation. The planet rotates on its side relative to its orbit around the Sun. This creates extreme seasonal patterns, unlike those experienced on Earth. During parts of its long-year regions near one pole receive continuous sunlight, while other regions remain in prolonged darkness. Uranus marks a significant step outward from the Sun. By this distance, sunlight has weakened considerably. The Sun itself appears smaller than it does from Earth, yet it still dominates the sky and remains the primary source of illumination and gravitational control. Farther still lies Neptune, the most distant major planet. Neptune shares some characteristics with Uranus, but possesses a deeper blue appearance and highly active weather systems. Powerful winds move through its atmosphere at remarkable speeds. Despite its great distance from the Sun, Neptune remains a dynamic world. For missions heading toward Pluto, Neptune often represents an important geographical marker. Beyond Neptune begins the region where Pluto spends most of its orbit. The giant planets gradually give way to the realm of icy bodies that populate the outer frontier of the solar system. The scale of this giant planet region helps explain why reaching Pluto requires so much time. The distance from Earth to Jupiter alone exceeds the separation between many destinations familiar to human exploration. Adding Saturn, Uranus, and Neptune reveals a chain of enormous intervals stretching outward from the Sun. A spacecraft must cross these regions before even approaching Pluto's neighborhood. The giant planets also reveal how the solar system stores much of its mass. Although the Sun contains the overwhelming majority, Jupiter and its companions account for most of what remains. Their gravitational influence shapes countless trajectories, affects smaller bodies, and helps define the architecture of the solar system itself. As a spacecraft moves through this region, communication delays continue increasing. Signals require longer periods to travel back to Earth. The Sun occupies a smaller portion of the sky. Familiar planetary landmarks become increasingly distant. The mission enters a realm where isolation grows steadily more apparent. Yet the giant planets are not merely obstacles separated by empty space. They are active worlds with complex atmospheres, extensive moon systems, and powerful gravitational fields. Their existence influences nearly every discussion of long-range travel. Understanding their position and influence is essential for understanding how humans might someday reach Pluto efficiently. The region of giant planets therefore serves as the great middle expanse of the solar system. It bridges the relatively compact inner planetary neighborhood and the distant frontier beyond Neptune. Here the scale expands dramatically. Gravity acquires new importance, and the true size of the solar system becomes increasingly evident. A spacecraft crossing this realm travels through some of the largest planetary systems, known steadily advancing toward the remote outer regions where Pluto waits in the cold sunlight of the distant frontier. The giant planets occupy enormous regions of space, but they offer more than landmarks along the route to Pluto. Their motion around the Sun creates opportunities that can dramatically influence travel time. A spacecraft does not always rely solely on the energy carried at launch. Instead, it can sometimes borrow a small portion of a planet's orbital momentum. This technique, known as a gravity assist, has become one of the most valuable methods in the history of deep space exploration. Gravity assist refers to the use of a planet's gravitational field to alter the speed and direction of a spacecraft. The spacecraft approaches a moving planet along a carefully calculated path. As it enters the planet's gravitational influence, the spacecraft accelerates toward the planet. It then curves around it and departs along a different trajectory. The interaction changes the spacecraft's motion relative to the Sun. At first glance, this process may appear to create energy from nothing. In reality, the laws of physics remain fully respected. The spacecraft gains energy by taking an extremely small amount from the planet's orbital motion. Because the planet is so massive, the effect on the planet is essentially undetectable. The effect on the spacecraft, however, can be significant. The principle resembles a moving object transferring momentum to another object. In everyday life, similar exchanges occur constantly, though usually on much smaller scales. In the solar system, planets themselves become participants in these exchanges. Their immense mass and high orbital speeds make them powerful tools for navigation. Without gravity assist, many famous missions would have required far more fuel or far longer travel times. The outer solar system is simply too large for many spacecraft to reach efficiently through propulsion alone. By using planetary motion strategically, engineers can achieve results that would otherwise be difficult or impossible. Jupiter plays a particularly important role in gravity assist missions. Because it is both massive and fast-moving in its orbit around the Sun, it can provide substantial changes in spacecraft velocity. Many missions bound for distant destinations have relied on encounters with Jupiter to gain speed and adjust direction. The timing of these encounters is critical. Planets move continuously around the Sun, so favourable alignments occur only during certain periods. Engineers often wait years for the proper configuration before launching a mission. A launch opportunity is therefore not simply a matter of having a spacecraft ready. It depends on the geometry of the solar system itself. For a mission to Pluto, timing can make a remarkable difference. A carefully planned gravity assist may shorten the journey by years. An unfavourable alignment may require a slower trajectory or a much greater expenditure of fuel. The movement of planets becomes part of the transportation system. The mathematics behind gravity assists belongs to the field of celestial mechanics. Engineers calculate trajectories with extraordinary precision. Tiny differences in timing or position can produce large differences after years of travel. Computers perform extensive simulations to determine how a spacecraft should approach a planet, and how the encounter will influence the remainder of the journey. The success of these calculations demonstrates one of the most remarkable achievements of modern science. Spacecraft launched from Earth can travel billions of kilometers and arrive at distant targets with extraordinary accuracy. This precision is possible because planetary motion follows predictable physical laws. Gravity assists also reveal an important truth about space travel. Speed is often more valuable than directness. A route that appears longer may actually be faster if it allows a spacecraft to gain momentum from a planetary encounter. The shortest geometric path is not always the most efficient trajectory. As a spacecraft approaches a planet for a gravity assist, its speed relative to the planet increases. The planet's gravity bends the spacecraft's path into a smooth curve. After passing through the encounter, the spacecraft departs with a new velocity relative to the Sun. The process can increase speed, decrease speed, or change direction depending on mission requirements. This flexibility makes gravity assists useful for many different objectives. Some missions need additional speed to reach distant targets. Others require slower velocities to allow detailed observations. The same physical principle can be applied in different ways depending on the desired outcome. The concept became especially important during the exploration of the outer planets. Spacecraft traveling toward Jupiter, Saturn, Uranus, and Neptune often used multiple gravity assists to extend their reach. Each encounter added momentum or redirected the trajectory, creating pathways through the solar system that would have been impractical using propulsion alone. A mission to Pluto benefits from the same approach. Pluto's distance makes every increase in velocity valuable. Even modest improvements can reduce travel time substantially when applied over billions of kilometers. The earlier the speed increase occurs, the greater the cumulative effect during the long voyage outward. Gravity assists do not eliminate the challenges of reaching Pluto. The destination remains extraordinarily distant. The spacecraft must still cross immense regions of space. Communication delays continue growing. Sunlight continues weakening. Yet gravity assists provide one of the most effective methods available for reducing travel time without requiring unrealistic amounts of fuel. The technique also highlights the interconnected nature of the solar system. Planets are not isolated worlds existing independently of one another. Their motion influences navigation throughout the system. A mission to Pluto may depend partly on the position of Jupiter years earlier. Events occurring across vast distances become linked through gravity and orbital motion. For future human missions, gravity assists would likely remain important. Human spacecraft carry greater mass than robotic probes, and therefore face even stricter energy requirements. Efficient use of planetary momentum could help reduce travel times and lower the amount of fuel needed for departure from Earth. The outer solar system rewards patience and precision. Gravity assists embody both qualities. They require careful planning long before launch and depend on predictable planetary motion unfolding over years. Yet when executed successfully, they transform the journey. A spacecraft gains speed not through additional engines or fuel, but through a brief encounter with a world already moving around the Sun. In this way, the planets themselves become partners in exploration. Their gravity helps open pathways across distances that would otherwise seem overwhelming. For any serious attempt to reach Pluto within a practical time frame, understanding and using these gravitational opportunities becomes one of the most important parts of the voyage. The question of how long it takes to reach Pluto receives its clearest answer from a spacecraft that has already completed the journey. Before any future human mission can be considered, it is useful to examine the fastest successful voyage ever made to Pluto. This voyage belongs to NASA's New Horizons mission, a robotic spacecraft specifically designed to explore the distant dwarf planet and its surrounding environment. New Horizons begins its journey in the year 2006. The spacecraft launches from Earth aboard a powerful rocket and immediately enters one of the fastest departure trajectories ever achieved by a planetary mission. From the moment it leaves, Earth's speed becomes the defining characteristic of the mission. Engineers recognize that Pluto is so distant that reducing travel time requires maximizing velocity from the earlier stages of flight. The spacecraft itself is relatively compact. Unlike a future human spacecraft, it carries no crew living quarters, food supplies or life support systems. Instead, it contains scientific instruments, communication equipment, computers, power systems, and propulsion components necessary for a long robotic mission. The absence of human passengers allows the spacecraft to remain comparatively light, making higher speeds easier to achieve. Even with this advantage, Pluto remains far away. New Horizons cannot simply travel directly to its destination at constant speed. The mission relies on careful trajectory planning and the gravitational environment of the solar system. Shortly after launch, the spacecraft begins crossing the planetary regions that separate Earth from Pluto. A key moment occurs when New Horizons encounters Jupiter. The giant planet provides a gravity assist that increases the spacecraft's velocity relative to the Sun. This encounter effectively shortens the total travel time by several years, compared with a trajectory that would not use Jupiter's gravitational influence. The spacecraft gains momentum without consuming large additional amounts of fuel. The Jupiter flyby also offers scientific opportunities. Instruments observe the giant planet, its atmosphere, and several of its moons. Yet these observations remain secondary to the primary purpose of the encounter. The main objective is speed. Every increase in velocity becomes valuable when the destination lies billions of kilometers away. After departing Jupiter, New Horizons enters the long outward crossing toward Pluto. For years, the spacecraft travels through increasingly remote regions of the solar system. During much of this period, there is little need for major course corrections. The spacecraft follows a carefully planned trajectory monitored from Earth and adjusted only when necessary. The vast majority of the mission unfolds quietly. Days become months, months become years. The spacecraft continues outward through deep space, while Earth and Pluto both move along their own orbital paths. The journey illustrates one of the defining characteristics of outer solar system exploration patience. Communication with New Horizons reflects the growing distances involved. Radio signals travel at the speed of light, yet the increasing separation between Earth and the spacecraft creates longer and longer delays. Commands transmitted from Earth require hours to arrive. Information sent back from the spacecraft also requires hours to complete the return journey. As New Horizons approaches Pluto, the spacecraft begins gathering increasingly detailed observations. What had once appeared as a tiny point of light gradually resolves into a complex world. Features on the surface become visible. Moons can be studied more carefully. The destination that had remained largely mysterious for decades begins revealing its structure. The closest approach occurs in the year 2015. The spacecraft reaches Pluto approximately 9.5 years after launch. This travel time becomes one of the most important facts in discussions about reaching Pluto. A robotic spacecraft launched with powerful propulsion and assisted by Jupiter's gravity requires nearly a decade to complete the journey. Even this impressive achievement represents a compromise between speed and practicality. Faster travel generally demands more energy. More energy often requires more fuel or more powerful launch systems. Engineers must balance performance against technical limitations, cost, and reliability. New Horizons achieves an unusually fast trajectory by the standards of planetary exploration, but it does not approach the theoretical limits permitted by physics. The scientific results of the mission transform understanding of Pluto. Images reveal mountains composed largely of water ice. Vast plains stretch across portions of the surface. Layers appear within the atmosphere. Evidence emerges of geological processes that continue shaping the dwarf planet despite its extreme distance from the Sun. Pluto proves far more complex than many scientists expected. Rather than a simple frozen relic, it displays a rich variety of landscapes and structures. The observations demonstrate that even distant worlds can remain active over long periods of time. The mission also highlights the difference between robotic and human travel. A robotic spacecraft can tolerate conditions that would be extremely challenging for human passengers. It does not require air-water food, sleep medical care, or protection from long-term isolation. It can operate for years with minimal intervention while enduring environments unsuitable for people. This distinction becomes crucial when considering future human missions. The nearly 10-year travel time achieved by New Horizons applies to a lightweight robotic probe. A human spacecraft would likely be much heavier. Additional mass generally makes acceleration more difficult and may increase mission complexity. The comparison does not mean human travel is impossible, but it demonstrates the scale of the challenge. New Horizons therefore provides a valuable benchmark. It shows that Pluto is reachable with existing technology. It demonstrates that a carefully planned mission can cross billions of kilometers and arrive with remarkable precision. At the same time, it reveals how long even a successful journey requires. The mission's duration also changes the way distance is perceived. Pluto is no longer merely a remote object observed through telescopes. It becomes a destination that has actually been visited. Yet the travel time remains measured in years rather than months. The spacecraft spends nearly a decade crossing the solar system before arriving at its target. For anyone seeking an answer to the question of how long it takes to reach Pluto, New Horizons offers the most direct example available. The journey is not hypothetical. It is a completed voyage carried out by a real spacecraft, moving through the actual environment of the solar system. Its experience provides a foundation for understanding both the possibilities and the limitations of deep space travel. After the orbit of Neptune, the solar system enters a region that feels increasingly remote from the familiar planetary environment surrounding Earth. This is the realm through which a spacecraft approaching Pluto must travel during the final portion of its outward journey. The distance from the Sun remains enormous. The major planets are left behind. The surroundings become quieter, darker, and more sparsely populated. Yet this region is not empty. It possesses its own structure, materials, and physical conditions that shape every voyage passing through it. Sunlight remains present throughout the outer solar system, but its character changes dramatically. Near Earth, sunlight dominates the sky and provides abundant energy. At Pluto's distance, the same sunlight has spread across a vastly larger volume of space. The Sun appears much smaller and far less bright. Daylight still exists, but its intensity is greatly reduced. This reduction follows a simple physical principle. As light moves away from its source, it spreads outward. The same amount of energy occupies an ever-expanding area. By the time sunlight reaches Pluto, only a small fraction of the energy available near Earth remains concentrated at any given location. For spacecraft, weaker sunlight creates practical consequences. Solar panels become less effective as distance increases. A spacecraft designed to operate near Pluto often requires an alternative source of electrical power. New Horizons, for example, relies upon a radioisotope power system that generates electricity from the natural decay of radioactive material. Such systems provide steady power even where sunlight becomes too weak for large-scale solar generation. Temperature also changes with increasing distance from the Sun. Space itself does not possess temperature in the same way that air or water does, but objects exposed to sunlight absorb energy and warm accordingly. With less solar energy available, spacecraft components tend to become colder. Engineers carefully design insulation heaters and thermal systems to ensure that instruments continue functioning properly. The outer solar system contains a thin distribution of dust particles. These particles originate from various sources, including collisions among small bodies and material released from comets. The density of dust remains extremely low. A spacecraft can travel vast distances without encountering significant amounts of matter. Nevertheless, sensitive instruments can detect these tiny particles and help scientists understand the environment of deep space. Cosmic rays also become increasingly important. Cosmic rays are high-energy particles arriving from distant regions of the galaxy and beyond. Earth's atmosphere and magnetic field provide substantial protection against many of these particles. Far from Earth, that protection is largely absent. Spacecraft traveling toward Pluto must operate in an environment where exposure to energetic radiation becomes a continuing concern. For robotic missions, radiation primarily affects electronics and instruments. Engineers develop systems capable of resisting damage and continuing operation despite long exposure. For future human missions, radiation would represent a far more significant challenge because living tissue is vulnerable to accumulated exposure over long periods. The region beyond Neptune is often associated with the Kuiper Belt. This broad collection of icy bodies extends across a vast area of the outer solar system. Pluto is one of its largest known members, but countless smaller objects also occupy this distant realm. Most remain separated by enormous distances despite belonging to the same general population. The Kuiper Belt provides important clues about the formation of the solar system. Many of its objects preserve materials that have experienced relatively little change since the earlier stages of planetary development. Their great distance from the Sun has allowed them to remain in a cold environment for billions of years. A spacecraft traveling through this region encounters an environment defined more by separation than by proximity. Individual objects exist, but the distances between them remain immense. Even within the Kuiper Belt, empty space dominates. The spacecraft spends most of its time moving through darkness, punctuated by occasional distant points of light. Navigation remains essential throughout this phase of the journey. Pluto continues moving along its orbit while the spacecraft advances toward the location where the encounter must occur. Small adjustments may be required to maintain accuracy. Even tiny corrections can prove important after years of travel across billions of kilometers. Communication delays become increasingly noticeable. Radio signals require several hours to travel between Earth and the outer solar system. Mission controllers cannot guide a spacecraft moment by moment. Instead, spacecraft must possess a significant degree of autonomy. Computers on board monitor systems, execute planned activities, and respond to certain situations without waiting for immediate instructions from Earth. The visual appearance of the solar system changes as well. The Sun becomes a brilliant star-like object rather than the dominant presence familiar from Earth. The major planets lie far behind. Earth itself becomes nearly impossible to distinguish without powerful instruments. The spacecraft enters a realm where the connection to its place of origin feels increasingly abstract. Despite the apparent emptiness, the outer solar system remains fully governed by the same physical laws operating near Earth. Gravity continues shaping orbits. Light continues traveling across space. Matter continues interacting according to predictable principles. The environment becomes more remote but not fundamentally different in its underlying physics. One of the most striking characteristics of this region is the passage of time. A spacecraft may spend years crossing the vast distances between Neptune and Pluto. During this period, progress is measured not by dramatic changes in scenery, but by the gradual reduction of an immense separation. Day after day, the spacecraft continues moving outward. Each hour adds distance from the Sun and brings Pluto slightly closer. The journey through deep space demonstrates that reaching Pluto is not merely a matter of technological capability, it is also a matter of endurance. The spacecraft must continue functioning reliably for many years. Systems must remain operational despite cold temperatures, radiation exposure, communication delays, and prolonged isolation. This outer region of the solar system therefore represents more than a geographical location. It embodies the long interval between departure and arrival. Here the spacecraft spends much of its voyage moving through sparse surroundings under faint sunlight. The environment is quiet, stable, and vast. It is the final great expanse that must be crossed before Pluto itself begins to dominate the mission. As the long journey through the outer solar system continues, Pluto gradually changes from a distant destination into an actual target. For most of the voyage, the spacecraft travels toward a world that appears only as a tiny point of light. Even after years of motion across billions of kilometers, Pluto remains visually small. The challenge of reaching it is not simply one of distance, it is also one of precision. A spacecraft must arrive at the correct place and at the correct time despite traveling through an immense volume of space. The difficulty becomes easier to appreciate when considering Pluto's size. Although large enough to be classified as a dwarf planet, Pluto remains much smaller than Earth. Its diameter is only a fraction of Earth's. Against the enormous scale of the solar system, it represents a comparatively small target, moving continuously along its orbit around the Sun. A spacecraft cannot aim toward the location where Pluto appears at launch. By the time the spacecraft arrives years later, Pluto will have moved. Engineers must instead calculate where Pluto will be in the future. The spacecraft is directed toward that future position, allowing both objects to arrive at the same place at the same time. This process relies upon detailed knowledge of orbital motion. Astronomers track Pluto's path with great accuracy using telescopes and mathematical models. Decades of observations make it possible to predict its future position with remarkable precision. Although small uncertainties always exist, the orbit is known well enough to support successful mission planning. The spacecraft itself is also tracked continuously. Radio signals exchanged with Earth allow engineers to determine its position and velocity. By combining these measurements with models of planetary motion, mission teams can evaluate whether the spacecraft remains on the desired trajectory. Even a very small deviation can become significant over time. Imagine a spacecraft that misses its intended course by only a tiny angle near Earth. After travelling billions of kilometres, that small error could place it far from Pluto. For this reason, navigation requires constant attention throughout the mission. Course corrections are generally performed using small thrusters. These engines produce modest amounts of force compared with the powerful rockets used during launch. Yet in deep space, even small adjustments can gradually alter a spacecraft's path. The earlier a correction is made, the less fuel is usually required. Approaching Pluto involves a gradual transition from long-range navigation to increasingly detailed targeting. At great distances, engineers focus on ensuring that the spacecraft remains broadly aligned with the intended trajectory. As Pluto grows larger in onboard images, navigation can incorporate direct observations of the target itself. The process resembles crossing an ocean toward a distant island. At first, only general direction matters because the island remains invisible. As the destination approaches, more precise adjustments become possible. In space, however, the scales are vastly larger and the consequences of error more significant. Communication delays complicate operations. By the time a signal reaches Earth, several hours may have passed since it left the spacecraft. A response requires additional hours. Real-time control is impossible. The spacecraft must therefore perform many activities independently according to carefully prepared instructions. Computers on board manage navigation tasks, monitor system health, and execute observation sequences. Engineers on Earth develop detailed plans well in advance. Commands are transmitted long before they're needed, allowing the spacecraft to carry out activities autonomously during critical periods. As Pluto approaches, scientific observations become increasingly important. Instruments begin collecting data that help refine knowledge of the dwarf planet's position and environment. Images reveal surface details with steadily improving clarity. What was once a point of light gradually becomes a recognizable world. The moons of Pluto also enter the picture. Charon, the largest moon, is especially significant because of its substantial size relative to Pluto. The two bodies orbit a common center of motion. Their gravitational relationship creates a dynamic system that must be understood when planning close observations. The spacecraft's speed remains a defining factor during approach. Missions like New Horizons travel so rapidly that they cannot simply stop upon arrival. Carrying enough fuel to slow down completely would require a much larger spacecraft. Instead, the mission is designed as a flyby. The spacecraft passes through the Pluto system at high speed, collecting data during a brief encounter before continuing outward. This reality highlights an important aspect of travel time. Reaching Pluto is one challenge, remaining there is another. A mission intended to enter orbit around Pluto would require additional energy for deceleration. Such a mission would likely involve different design choices and potentially longer overall timelines. The approach phase also reveals the cumulative value of precision. Every calculation made years earlier contributes to the success of the encounter. Launch timing, gravity assists, course corrections, and navigation measurements all work together to ensure arrival at the correct location. The encounter lasts only a short time compared with the years of travel required to reach it. From the spacecraft's perspective, Pluto gradually transforms from an abstract destination into a landscape. Surface features emerge. Variations in brightness become visible. Geological structures can be distinguished. The destination that once existed only in calculations and telescope observations becomes a real place. Yet the vastness of the solar system remains evident throughout the approach. Even after years of travel, Pluto occupies only a small region within an enormous expanse of space. The achievement lies not merely in crossing the distance, but in doing so with sufficient accuracy to arrive at a moving target billions of kilometers from Earth. Approaching Pluto therefore represents the culmination of a long navigational effort. The challenge is not brute force alone. It is precision maintained over extraordinary distances and timescales. The spacecraft spends years moving through deep space so that at one carefully calculated moment its path intersects the orbit of a small icy world, travelling through the distant reaches of the solar system. The successful arrival of a spacecraft at Pluto demonstrates that the journey is possible, but it also reveals why the voyage requires so much time. The answer is not found in a single limitation. Instead, it emerges from several physical realities working together. Distance energy, fuel mass gravity, and orbital motion all contribute to the duration of the trip. Understanding these constraints helps explain why even advanced spacecraft need years to reach the outer solar system. The most obvious factor is distance itself. Pluto orbits billions of kilometers from Earth. Regardless of technological sophistication, every kilometer must still be crossed. A faster journey requires greater velocity, and greater velocity generally requires more energy. The relationship between speed and energy becomes increasingly demanding as missions seek shorter travel times. Energy serves as the foundation of space travel. Rockets accelerate by expelling propellant, creating motion through the conservation of momentum. To travel faster, a spacecraft must either carry more propellant, use it more efficiently, or rely upon additional sources of energy. Each option introduces challenges. Carrying more propellant increases mass. Increased mass requires more energy to accelerate. More energy often demands more propellant. This relationship creates a cycle that engineers must carefully manage. Adding fuel can improve performance, but only up to a point. Beyond that point, the added mass may reduce the expected benefit. This challenge is described by the rocket equation, one of the central principles of astronautics. Although the mathematics behind it can be complex, the practical meaning is straightforward. Achieving higher speeds requires disproportionately larger amounts of propellant. Small increases in velocity may demand significant increases in fuel. The result is that spacecraft design becomes an exercise in compromise. Engineers seek the best balance between payload fuel, structural mass, scientific instruments, and mission objectives. Every kilogram must justify its presence because mass influences nearly every aspect of performance. Gravity also contributes to travel time. Spacecraft do not move through an empty environment free from forces. The Sun exerts a powerful gravitational influence throughout the solar system. Planets contribute their own effects. A spacecraft heading toward Pluto must navigate within this gravitational landscape. The Sun's gravity continuously pulls inward. Even as a spacecraft moves outward, it remains bound to the solar system. The vehicle follows an orbit around the Sun rather than escaping entirely. Energy is required not only to increase speed, but also to move into larger and more distant solar orbits. Orbital mechanics introduces another important reality. The shortest distance between two locations is not always the fastest route. Spacecraft travel along trajectories determined by gravity and momentum. Efficient paths often involve carefully shaped curves rather than direct lines. Time is therefore influenced by geometry as well as speed. Planetary alignment plays a role too. Favorable configurations can reduce travel time through gravity assists or more efficient trajectories. Less favorable alignments may require additional energy or longer flight durations. The positions of planets become part of the transportation system. Communication considerations add another layer. As distance increases, signals require longer periods to travel between Earth and the spacecraft. Although communication delays do not directly increase travel time, they affect mission operations. Spacecraft must often function independently because immediate guidance from Earth becomes impossible. Reliability also shapes mission design. A spacecraft traveling to Pluto must operate for many years. Systems must remain functional throughout the voyage. Engineers often favor proven technologies over riskier alternatives because reliability becomes critical during long missions. A slightly slower but dependable approach may be preferable to a faster method with greater uncertainty. Human missions would face additional constraints. A robotic spacecraft can tolerate conditions that would be unacceptable for people. Human travelers require life support, radiation, protection, food, water, waste management, medical resources, and living space. These requirements increase mass substantially. More mass generally means lower acceleration for a given amount of propellant. As a result, a human spacecraft traveling to Pluto would likely face greater energy demands than a robotic probe. Engineers would need to account for these factors when estimating travel times. Radiation protection provides a useful example. Deep space contains energetic particles capable of damaging living tissue. Shielding can reduce exposure, but shielding materials add weight. Additional weight influences propulsion requirements. The need to protect human occupants therefore affects the overall architecture of the mission. Another factor is deceleration. A flyby mission can arrive at Pluto without stopping. An orbital mission requires additional energy to slow down. A landing mission would require even more. Each objective imposes new demands that influence travel time and spacecraft design. Current chemical rockets, despite decades of refinement, possess inherent limitations. They are highly effective for leaving Earth and conducting many planetary missions, but they do not provide unlimited performance. The energy stored in chemical reactions is finite. Reaching dramatically higher speeds may require different propulsion methods. Yet even if more advanced propulsion becomes available, some constraints remain. Greater speed often means greater engineering complexity. Higher energy systems may require larger power supplies, additional safety measures, or new materials capable of operating under demanding conditions. Technological advances can reduce travel time, but they rarely eliminate challenges entirely. The history of exploration repeatedly demonstrates this pattern. Improvements in technology shorten journeys that once seemed impossibly long. However, every gain introduces new questions involving cost, reliability, safety, and practicality. The balance between these factors shapes mission planning. Pluto occupies a distant region of the solar system, where these realities become particularly visible. The voyage is long not because engineers lack skill, or because spacecraft are poorly designed. It is long because the destination is genuinely far away, and because the laws of physics impose specific requirements on movement through space. Understanding these constraints helps place travel times in context. A journey lasting years may initially seem slow compared with transportation on Earth. Yet when considered against the scale of the solar system, such travel times reflect remarkable achievements. Spacecraft cross billions of kilometers, navigate with extraordinary precision, and arrive at distant worlds using technologies developed on a small planet orbiting an ordinary star. The surprising truth about reaching Pluto is therefore not that it takes a long time. The surprising truth is that humanity can reach it at all. The constraints are real and unavoidable, but careful engineering, scientific understanding, and patient planning make the journey possible despite the immense challenges imposed by distance and physics. Although current missions to Pluto require many years of travel, scientists and engineers continue studying propulsion systems that could shorten the journey. These concepts range from technologies already operating in space to advanced systems that remain under development. Some are practical extensions of existing methods. Others depend upon breakthroughs that have not yet been achieved. Together they illustrate how future spacecraft might reduce travel times, while remaining consistent with established physical laws. The most familiar propulsion method is the chemical rocket. Chemical propulsion has carried astronauts to the Moon, launched planetary probes throughout the solar system, and remains the foundation of modern spaceflight. Its strengths include reliability, simplicity, and the ability to produce large amounts of thrust quickly. Thrust refers to the force that pushes a spacecraft forward. Chemical rockets excel at generating high thrust during launch and major maneuvers. However, they consume propellant rapidly and are limited by the amount of energy available in chemical reactions. These limitations help explain why journeys to Pluto remain measured in years. One alternative already in use is ion propulsion. An ion engine accelerates electrically charged particles to extremely high speeds and expels them from the spacecraft. The resulting thrust is very small compared with a chemical rocket, but it can operate continuously for long periods. The advantage of ion propulsion lies in efficiency. A spacecraft can achieve substantial changes in velocity while using relatively small amounts of propellant. Several successful missions have demonstrated this capability. Over months and years, gentle, continuous acceleration can produce significant results. For travel to Pluto, ion propulsion offers interesting possibilities. A spacecraft equipped with sufficient electrical power could gradually increase its speed throughout much of the journey. The challenge lies in providing the necessary energy. Far from the sun, solar power becomes less effective, so alternative power sources would likely be required. Nuclear propulsion represents another area of active study. Nuclear systems contain far more energy per unit mass than chemical fuels. Several different approaches have been proposed over the decades. One concept is nuclear thermal propulsion. In this system, a nuclear reactor heats a propellant such as hydrogen. The hot gas expands through a nozzle producing thrust. The basic principle resembles a chemical rocket, but the energy source is different. Studies suggest that nuclear thermal propulsion could provide higher efficiency than conventional chemical systems. Another concept involves nuclear electric propulsion. Here, a reactor generates electricity that powers ion engines or similar systems. This approach combines the high energy density of nuclear power with the efficiency of electric propulsion. Such systems could potentially support long-duration missions across the solar system. Research continues in these areas, but significant engineering challenges remain. Reactors must operate safely and reliably in space. Heat must be managed effectively. Systems must remain functional for many years. While the underlying physics is well understood, practical implementation requires extensive development. More ambitious concepts have also been proposed. Fusion propulsion is one example. Fusion is the process that powers stars, including the Sun. It involves combining light atomic nuclei to release energy. If controlled fusion can eventually be harnessed for spacecraft propulsion, it could provide access to much greater energy levels than current technologies. At present, however, fusion remains an area of ongoing research. Experimental facilities on Earth continue investigating methods for achieving sustained and practical fusion reactions. Whether fusion propulsion will become feasible for spacecraft remains uncertain. Antimatter propulsion has occasionally appeared in scientific discussions as well. When matter and antimatter meet, they release large amounts of energy. In theory, this energy could support extremely powerful propulsion systems. In practice, producing and storing antimatter remains extraordinarily difficult. Current technology can create only tiny quantities, and the challenges associated with long-term storage are substantial. Because of these difficulties, antimatter propulsion remains largely a theoretical possibility, rather than a practical near-term solution. Some proposals focus not on carrying energy, but on receiving it from external sources. Laser propulsion is one example. In this concept, powerful lasers located elsewhere direct energy toward a spacecraft. The spacecraft uses that energy to accelerate without carrying all of its fuel on board. Laser-based concepts have attracted interest for very small spacecraft, particularly those intended for interstellar research. Applying similar principles to large human spacecraft would require enormous infrastructure and technological advances. Nevertheless, the idea illustrates the variety of approaches being explored. Despite these possibilities, important physical limits remain. No known technology allows travel faster than light. According to current scientific understanding, the speed of light represents a fundamental limit in nature. Future propulsion systems may dramatically reduce travel times within the solar system, but they do not eliminate the underlying constraints imposed by physics. The practical question therefore becomes one of improvement rather than complete transformation. Could a mission that currently requires nearly 10 years be reduced to 5 years? Could 5 years become 3? These are the types of goals that motivate ongoing research. Human missions especially benefit from shorter travel times. Reduced duration decreases exposure to radiation, lowers the amount of food and supplies required, and may lessen some of the psychological challenges associated with prolonged isolation. Faster transportation therefore offers advantages beyond simple convenience. At the same time, reliability remains essential. A propulsion system intended for deep space travel must function consistently for years. Extraordinary performance is valuable only if it can be achieved safely and predictably. Engineers therefore evaluate new technologies not only by their speed but also by their practicality. The history of space exploration shows steady progress rather than sudden leaps. Early spacecraft reached orbit. Later missions reached the Moon. Robotic probes expanded humanity's reach across the solar system. Each advancement built upon previous achievements. Future propulsion systems are likely to follow a similar pattern, emerging gradually through decades of research and testing. Pluto remains a useful benchmark for these efforts because of its great distance. Any meaningful improvement in propulsion becomes visible when measured against the long journey to the outer solar system. The dwarf planet serves as a test of how effectively new technologies can reduce travel times across vast distances. Observations and engineering studies indicate that significant improvements are possible. It remains uncertain exactly which technologies will prove most successful in future decades. What is clear is that researchers continue exploring ways to move faster, more efficiently and more reliably through the solar system. The long voyage to Pluto provides both a challenge and a motivation for that ongoing work. If a robotic spacecraft can travel to Pluto with little more than instruments, computers, power systems and communication equipment, a human mission introduces a very different set of requirements. The destination remains the same, and the distance remains the same, but the presence of people transforms the nature of the spacecraft. A journey lasting years requires not only transportation, but also a functioning environment capable of sustaining human life throughout the voyage. Life support becomes the most immediate consideration. Human beings require air, water, food, and stable temperatures. On Earth, these necessities are provided naturally by the environment. In deep space, every requirement must be supplied or carefully recycled within the spacecraft itself. Air management involves maintaining the proper mixture of gases for breathing, while removing carbon dioxide produced by the crew. Water must be conserved and reused whenever possible. Modern spacecraft already employ recycling systems, but a mission to Pluto would require far greater efficiency because resupply from Earth would be impossible. Food presents another challenge. A journey lasting many years requires either carrying substantial food reserves or developing methods for producing at least part of the food supply during the mission. Both approaches involve trade-offs. Stored food increases mass. Food production systems require equipment, energy, and maintenance. The spacecraft must also provide living space. Humans are not machines designed to remain motionless for years. Crews require room to sleep, work, exercise, and perform daily activities. The amount of available space influences physical health and psychological well-being. Designing an environment that remains livable over long periods becomes a major engineering task. Microgravity introduces additional concerns. Prolonged exposure to weightlessness affects muscles, bones, and other bodily systems. Astronauts aboard orbital stations exercise regularly to reduce these effects. A mission lasting many years would require effective strategies for maintaining physical health throughout the voyage. One proposed solution involves artificial gravity. Artificial gravity refers to the creation of forces that mimic gravity through rotation. If part of a spacecraft rotates, occupants inside may experience a sensation similar to gravity. Various designs have been studied, though none has yet been implemented on a large interplanetary spacecraft. Radiation protection represents one of the most serious challenges. Beyond Earth's magnetic field, astronauts are exposed to energetic particles originating from the Sun and from distant regions of the galaxy. Over months and years, this exposure can increase health risks. Shielding can reduce radiation levels, but shielding materials add mass. Water fuel and specialized protective materials may all contribute to protection. Engineers must balance safety against the increased propulsion requirements associated with additional weight. The farther a spacecraft travels from Earth, the more independent it must become. Communication delays measured in hours prevent immediate assistance from mission control. The crew must possess the skills, equipment, and resources needed to address many problems without rapid support from Earth. Medical care, therefore, becomes another important consideration. During a mission lasting years, illnesses or injuries may occur. A spacecraft heading toward Pluto would likely require advanced medical equipment and crew members trained to handle a wide range of situations. The level of self-sufficiency required would exceed that of most previous human missions. Maintenance occupies a significant portion of long-duration spaceflight. Machines wear down, components fail, systems require inspection and repair. A spacecraft operating for many years must carry spare parts, tools, and diagnostic equipment. Reliability remains essential, but complete elimination of failures cannot be assumed. Psychological health is equally important. Deep space travel involves prolonged isolation from Earth. Communication delays limit direct interaction with people at home. The crew would spend years within a confined environment while knowing that immediate return is impossible. Studies conducted aboard space stations and in isolated environments on Earth provide valuable insights into these challenges. Observations indicate that social dynamics, workload management, personal privacy, and meaningful activities all contribute to long-term well-being. Future interplanetary missions would need to incorporate lessons learned from these experiences. The visual environment also changes during the journey. Near Earth, astronauts can observe the planet directly. As distance increases, Earth gradually shrinks into a bright point of light. Eventually, it becomes difficult to distinguish without optical assistance. The psychological effect of this growing separation remains an active area of study. Power generation is another essential system. A human spacecraft requires electricity for life support, communication, computing, lighting, environmental control, and many other functions. At Pluto's distance, sunlight is weak, making large solar arrays less practical. Nuclear power systems are often considered strong candidates for supporting long-duration missions in the outer solar system. Waste management may seem less dramatic than propulsion or navigation, but it becomes critically important during extended missions. Air, water, and biological waste must be handled efficiently to maintain a healthy environment. closed-loop systems that recycle resources help reduce the total mass that must be launched from Earth. Mission duration influences nearly every design decision. A spacecraft intended for a voyage lasting several years differs significantly from one designed for decades. Faster travel times reduce some challenges, but they do not eliminate them. Even relatively short interplanetary missions require extensive planning and robust systems. The concept of a spacecraft as a vehicle gradually gives way to the concept of a spacecraft as a habitat. During a journey to Pluto, the spacecraft becomes the crew's entire world. It provides protection, resources, medical support, living space, and transportation simultaneously. This transformation helps explain why human missions are more complex than robotic missions. The challenge is not simply reaching Pluto. The challenge is carrying a small, self-contained human environment across billions of kilometers while maintaining safety and functionality for years. Every kilogram of equipment serves a purpose, and every system contributes to the survival of the crew. The long voyage to Pluto therefore becomes an exercise in sustaining life as much as in covering distance. The spacecraft must function as a miniature ecosystem operating far from Earth. Success depends not only on speed and propulsion, but also on the ability to preserve human health and well-being throughout one of the longest journeys ever attempted. When engineers and scientists consider the possibility of sending humans to Pluto, they enter a realm that extends beyond current mission planning. No crewed expedition to Pluto has been approved, and no spacecraft capable of carrying people there currently exists. Yet the physical principles governing such a mission are well understood. By combining what is known about propulsion, life support, radiation protection, and orbital mechanics, it is possible to estimate what a realistic human journey might require. The first reality is that a crewed mission would almost certainly differ significantly from New Horizons. The robotic spacecraft succeeds because it is compact, lightweight, and designed primarily for observation during a flyby. Human travelers would require a much larger vehicle containing living space supplies, power systems, shielding, and equipment necessary for long-term survival. One possible mission architecture involves a large spacecraft assembled in Earth orbit. Components could be launched separately and connected in space. This approach avoids the difficulty of launching an extremely large spacecraft in a single piece. Similar concepts have been studied for future missions to Mars and other distant destinations. The completed spacecraft would then depart Earth using a propulsion system capable of supporting deep space travel. If chemical propulsion alone were used, travel times might extend well beyond those achieved by lightweight robotic probes. The greater mass of a crewed vehicle makes acceleration more difficult, increasing the importance of efficient propulsion methods. More advanced systems, such as nuclear thermal or nuclear electric propulsion, could potentially reduce travel times. Studies suggest that these technologies may provide meaningful improvements compared with conventional chemical rockets. The exact performance of future systems remains uncertain because such spacecraft have not yet completed operational missions to Pluto. Mission planners generally seek shorter travel times whenever possible. Every additional year in space increases demands on life support systems, radiation protection, maintenance requirements, and crew endurance. A voyage lasting several years is challenging. A voyage lasting decades would be even more difficult. The distinction between a flyby mission and an orbital mission becomes particularly important when people are involved. A flyby would allow the spacecraft to reach Pluto more quickly, because it would not need to carry enough fuel for major deceleration upon arrival. However, the time available for direct exploration would be limited. An orbital mission would permit extended scientific study. The spacecraft could remain near Pluto, observe the dwarf planet over long periods, and potentially support additional exploration activities. Yet entering orbit requires substantial energy. Additional propulsion systems and fuel would be necessary, increasing overall mission complexity. Some concepts have considered the possibility of using local resources found elsewhere in the solar system to support future exploration. Such ideas remain speculative in the context of a Pluto mission. Observations indicate that Pluto contains abundant ice and frozen compounds, but practical methods for using those materials to support a human expedition have not been demonstrated. Communication delays remain unavoidable. Even with advanced technology, messages traveling between Earth and Pluto are limited by the speed of light. Crews would experience delays measured in hours. Mission operations would therefore require a high degree of autonomy. The spacecraft itself would likely function as a small community. Crew members would live and work together for extended periods. Responsibilities would include navigation, maintenance, scientific activities, medical care, and daily operation of life support systems. Long-duration cooperation would be essential. Radiation exposure would remain one of the central concerns. Protective shielding could reduce risk, but complete elimination of exposure is unlikely. Mission duration therefore becomes closely connected to crew safety. Faster transportation systems would provide benefits not only by reducing travel time, but also by limiting cumulative radiation exposure. Psychological factors would also influence mission planning. The immense distance from Earth creates a unique environment. Unlike missions in Earth orbit or even future expeditions to Mars, a journey to Pluto would involve years spent traveling toward a destination that remains extraordinarily remote. The crew would operate with limited direct interaction with Earth and no possibility of rapid return. Power generation would require careful consideration. At Pluto's distance, sunlight is weak. Large solar arrays could contribute, but many studies favor nuclear power systems for operations in the outer solar system. Such systems offer reliable electricity independent of solar intensity. The overall timeline of a human Pluto mission depends heavily on propulsion technology. Using systems similar to those available today, travel times measured in many years appear likely. More advanced propulsion could shorten the journey, but the extent of future improvements remains uncertain. Observations and engineering studies indicate that reaching Pluto is physically possible within the known laws of nature. The challenge lies not in overcoming impossible barriers, but in solving numerous practical problems simultaneously. Propulsion, life support, radiation protection, reliability, and mission cost must all be addressed. The history of exploration provides useful perspective. Destinations once considered unreachable often become accessible as technology advances. The Moon, once an object observed only from afar, eventually received human visitors. Robotic spacecraft now travel routinely to worlds that earlier generations could only imagine exploring. Pluto may follow a similar path over very long timescales. Whether human explorers eventually visit the dwarf planet remains unknown. Technological progress, economic priorities, scientific goals, and societal decisions will all influence future developments. What can be said with confidence is that the journey would require extraordinary preparation and patience. The surprising truth about a human mission to Pluto is that the greatest challenge may not be the destination itself. Pluto already exists within humanity's reach, in the sense that robotic spacecraft have successfully traveled there. The greater challenge is creating a spacecraft capable of sustaining human life across the immense distances involved while maintaining acceptable levels of safety and reliability. A future crew departing for Pluto would therefore undertake one of the longest and most demanding voyages ever attempted. The mission would combine transportation, habitation, engineering, medicine, and exploration into a single undertaking. Every aspect of the spacecraft would be shaped by the reality of distance. The destination would remain a small, icy world on the far frontier of the solar system, but the journey required to reach it would be among the most ambitious projects in human history. At the largest scale, the journey to Pluto appears to be a simple matter of crossing billions of kilometers. Yet when the voyage is examined more closely, the total travel time emerges from countless smaller details. Every stage of the mission from launch to arrival contributes a small portion to the final duration. The surprising truth about reaching Pluto is found not only in the immense distance involved, but also in the accumulation of many practical realities that shape the pace of exploration. The launch itself occupies only a brief period compared with the overall mission. A rocket leaves Earth within minutes, yet years of preparation precede that moment. Engineers design spacecraft test components, analyze trajectories, and evaluate risks. While these activities occur before the spacecraft begins moving toward Pluto, they are part of the broader process required to make the journey possible. After launch, navigation becomes a continuing responsibility. A spacecraft does not simply travel unattended from Earth to Pluto. Instruments monitor orientation, computers track performance, engineers compare observations with predictions. Small adjustments help maintain the intended trajectory. Each correction may require only modest amounts of fuel, but together they contribute to the success of the mission. The accuracy required is remarkable. Pluto occupies a tiny region within an enormous volume of space. The spacecraft must arrive at the correct place after traveling for years. Tiny uncertainties in position, velocity, or timing must be identified and managed long before they can grow into larger problems. Communication introduces another layer of complexity. Radio signals require increasing amounts of time to cross the growing distance between Earth and the spacecraft. During the later stages of the journey, messages may require several hours to travel in one direction. Mission planning therefore becomes an exercise in anticipation. Commands are often prepared well in advance. Engineers consider future conditions and create detailed sequences of activities. The spacecraft then executes these instructions autonomously when the appropriate time arrives. This method allows operations to continue despite long communication delays. Data transmission also affects mission timelines. Scientific instruments can collect large amounts of information, but communication rates decrease with distance. Sending data across billions of kilometers requires patience. Information gathered during an encounter may take months to return fully to Earth. The New Horizons mission provides a useful example. The spacecraft gathered extensive observations during its flyby of Pluto, yet the complete transmission of scientific data continued long after the encounter itself. The speed of light imposes one limit on communication, while the strength of the signal and the capacity of communication systems introduce additional constraints. Power management contributes to mission operations as well. Every instrument consumes energy. Communication systems require power. Computers and heaters require power. Engineers must balance available resources against mission objectives. Careful scheduling ensures that essential systems remain operational throughout the voyage. Thermal control represents another ongoing concern. Spacecraft experience changing environmental conditions as they move through the solar system. Equipment must remain within acceptable temperature ranges despite prolonged exposure to cold environments. Heaters, insulation, and thermal design all contribute to maintaining functionality. Reliability depends upon attention to seemingly small details. A valve sensor computer chip or communication component may appear insignificant when viewed individually, yet the failure of a single critical element can affect an entire mission. Engineers therefore devote considerable effort to testing and redundancy. Redundancy means providing backup systems capable of performing important functions if primary systems fail. While redundancy improves reliability, it also increases mass. Additional mass influences propulsion requirements. Once again, the mission becomes a balance among competing factors. Time itself becomes a resource. During a voyage lasting many years, opportunities arise and disappear according to the positions of planets and spacecraft. Navigation maneuvers must occur at specific moments. Scientific observations must be scheduled appropriately. Delays may affect later activities. Mission planning, therefore, involves careful coordination across long timescales. Human missions would add further layers of complexity. Crew schedules, medical monitoring exercise programs, maintenance tasks, and psychological support would all require ongoing attention. The spacecraft would function not merely as a vehicle, but as a continuously operating environment. At the deepest level, travel time is determined by the laws of physics. Distance cannot be ignored. Signals cannot exceed the speed of light. Mass requires energy to accelerate. Gravity shapes motion throughout the solar system. These principles operate regardless of technological sophistication. Future advances may reduce travel time significantly. More efficient propulsion systems may allow higher velocities. Improved power generation may support new mission architectures. Better materials may reduce mass while maintaining strength. Yet the fundamental realities of distance and motion remain. The question of how long it would really take humans to reach Pluto therefore has no single universal answer. The result depends on propulsion technology, spacecraft design, mission objectives, and the level of acceptable risk. A future mission might require fewer years than current robotic voyages. It might require more. What remains consistent is the extraordinary scale of the undertaking. Pluto exists on the distant frontier of the solar system. Reaching it demands patience measured not in days or weeks, but in years. Every stage of the journey reflects a combination of engineering skill and physical reality. Launch energy, gravitational trajectories, communication delays, life support requirements, navigation precision, and system reliability all contribute to the final timeline. The surprising truth is not simply that Pluto is far away. The surprising truth is that the journey becomes possible through the successful coordination of countless details, each governed by the same physical laws operating throughout the universe. A spacecraft reaches Pluto not because distance becomes small, but because every challenge is addressed carefully and methodically over time. When viewed from Earth, Pluto appears as a faint point of light near the edge of the known planetary system. When viewed through the lens of exploration, it becomes a destination that reveals the scale of the solar system itself. The length of the journey reflects the vastness of that scale, and the remarkable ability of human knowledge to navigate across it. The voyage to Pluto unfolds slowly when measured against human expectations, yet it remains a brief event when compared with the age of the solar system. For billions of years, Pluto follows its quiet path around the Sun, completing each orbit over spans of time that exceed multiple human lifetimes. Against this vast backdrop, even a journey lasting many years becomes a small moment within a much larger story. The spacecraft travels through regions where sunlight grows faint and distances become difficult to imagine. The planets spread across enormous intervals. Signals cross space at the speed of light and still require hours to arrive. Gravity guides every movement. Momentum carries the spacecraft onward. The laws of nature remain constant from Earth to the distant frontier. Pluto itself remains a small icy world surrounded by darkness and cold sunlight. Mountains of ice rise above frozen plains. Moons travel alongside it through the outer solar system. It continues its slow orbit regardless of whether visitors arrive. The dwarf planet simply occupies its place within the larger structure of the solar system. Human exploration reveals that remoteness does not mean impossibility. A destination may be distant without being unreachable. The challenge lies in patience, preparation, and understanding. Each improvement in technology shortens some journeys and expands the range of places that can be explored. For now, Pluto remains one of the farthest worlds ever visited by spacecraft. Reaching it requires years of steady travel. A future human mission would likely require years as well, though perhaps fewer than today. The exact timeline remains uncertain. The scale of the challenge remains clear. The solar system stretches outward from the warmth of the sun to distant regions where light is dim and worlds are widely scattered. Pluto occupies one of those remote places quietly circling the sun, while carrying the history of planetary formation within its frozen landscapes. The journey toward it is ultimately a journey through distance itself, revealing how large the solar system truly is, and how far human exploration has already come.